afternoon. Thank you for taking the time to come over to the seminar, and thank you for the introduction. As you all know, I'm an assistant professor at Florida Atlantic University. I just started less than a month ago. Glad to get a change of scenery here in the Tampa area. It's definitely different and for the better than the Miami and Fort Lauderdale area. Less crowded and more laid back. So before I talk more about my research and projects, let's just give you a little bit of introduction about the university that I work in. We're growing pretty rapidly, and this is currently sitting at about 30,000 students. We have a goal of growing to up to 35,000 students. The breakdown is roughly 25,000 undergraduates and 5,000 graduate students. We have 5 satellite campuses. I actually have an office in one of the satellite campuses where I will be also storing some of my test vehicles that I will be purchasing. You can see this is a pretty new campus, and this is an aerial image taken back in about a year ago, and you can see there was still construction for a new parking garage as well as a new football stadium. Now it's been completed for this fall semester, and things have been rapidly changing. And we're also nicely located in Boca Raton, Florida, which is literally just less than 2 miles from the Atlantic coast. And it's got beautiful beaches right around campus. And we are a department in the civil engineering department of 15 faculty, 2 in transportation, and we are looking to expand and add at least one more faculty member for our transportation program, potentially 2. So here's just a quick overview of my group. I currently have 1 graduate student, and there will be 5 more coming in the spring semester. And I've already kicked off with some some projects with the FEOT, and I have a collaborative project with UC Berkeley that's funded by the Department of Energy. Primarily do a lot of simulation, and I use both the popular softwares Amazon and Visum. There will be a fleet of vehicles coming for my lab. I will be testing adaptive cruise control, dedicated short-range communication, so that's coming up in November, as early as October, but most likely November. And the introduction was enough information to get you to know me about my background, but let me just tell you a little bit more about myself. And I've actually been a pretty big fan of traveling around different states and a lot of the road trips and traveling by car. So I've actually been to 34 different states. The ones in orange are the ones that I actually lived in. So I grew up in Pennsylvania, moved to California in my teenage years, and went to school in Illinois and had some internships in Texas. Now I'm in my 5th state of Florida. I'm also looking forward to visiting some other states that are left blank at the moment, so down in the south and up in the northeast in the next few years.
But how did you get to Florida from California without passing through at least Louisiana?
Oh, I went through Colorado, actually. I
Okay.
went through Colorado, Kansas, Missouri, and then down through Atlanta.
Got it.
So that it took a little bit of a detour with this cross-country move. Good question, by the way. And you can see why I mean, I took a picture of my odometer literally like last night, and you can see why over the past 5.5 years or so, I put about 136,000 miles on my car. So a lot of miles. So transportation is really important to me because of my travels and my adventures. I really appreciate the highway network that we have here in the United States, especially when I go out to the western states where they're really remote. And in fact, I've actually been to most of the national parks out in the western states. You don't really see that kind of, divided 4-lane highways in rural Wyoming, for example, or Montana. To do a comparison, if you go out to other developed countries like Canada and Australia, in these really remote places, that is something that you cannot take for granted. But despite the appreciation, but nothing is all perfect. There are still challenges. If we look at the national level, and this is kind of an older statistic from the Bureau of Transportation Statistics, many people, there's still a lot of fatalities, 35,000 every year, as a result of crashes and 6.3 million crashes that we're dealing with every year, and that hasn't been going down, even in 2019. In terms of congestion, we're wasting 6.9 billion hours as a result of people sitting in traffic, and that equates to $160 billion of productivity lost if you do some conversion with the value of time. And because I'm going to be talking about emissions, I'm going to stress that the environmental impact of transportation is pretty severe here in this country as a result of congestion. We're looking at about 3.1 billion gallons of fuel being wasted, and that equates to 56 billion pounds of additional CO2 emitted to the atmosphere. So, national level, there are a lot of challenges and issues, but what about Florida? This is the every 10-year update from the Bureau of Transportation Statistics for individual states. Although the population here is not up to date, but we have grown past 20 million here in the state of Florida. In fact, we have surpassed the state of New York, now the third most populated state in the country. And we have been seeing a lot of growth in employment opportunities, as well as the number of vehicles and licensed drivers. So how do we move all these people, right? On an everyday basis, when people get to work, we're looking at about 80% of the people who drive alone. That's about the national average. And for carpools, roughly 10%. So do the math. If you look at this, almost 90% of the trips, or at least the commute trips, are done by car. So there's a lot of emphasis on making sure that the highway runs as efficiently as possible. And despite the fact that there's push for alternative modes, this is still our bread and butter. And in addition to moving people, we also have to move a lot of goods, because I'm in the Miami area, and this is the gateway to the United States for a lot of Latin American countries. And there's a lot of freight traffic here in the state of Florida. 1 trillion tons, that's worth about $1 billion. And doing all of that with a rather limited budget, we're doing better than many other states across the country, but we're still running a deficit on transportation funding after taking into account the gas taxes and tolls and other sources of revenue that we take for transportation. So with all these challenges, we have three primary objectives. Like what I said in the introduction to the national level issues, mobility issues, congestion, safety, and also environmental impact. So we want to reduce emissions as well. How have we done this in the past? Not in a particularly efficient way back in the 20th century. The common solution back in the 20th century is to build more transportation infrastructure. Let's build more highways especially, to build our way out of our problems. And that certainly hasn't happened. That has cost a lot of money. You can see the example of Houston, which they try to build more highway. In fact, they have the widest freeway in the entire country. Interstate 10 west of Houston, I believe it has about like 10 lanes in one direction for some segments. But that's not really solving the congestion problem. The congestion still exists. We still haven't seen a significant reduction in terms of fatalities. And obviously, having more cars drive on the highways is not going to really help you for reducing emissions and environmental impact. So in the 21st century, we want to start focusing and really put a lot more effort on managing our transportation infrastructure better. And to quickly define the phrase traffic management, this is a definition from TRV. It really, to break this down, it just involves control and guidance, arrangement, and organization of different modes of transportation. That includes bicyclists and pedestrians, and to achieve primarily three main objectives. We want to be safe, and we also want to be efficient, and also enhance the quality of the local environment. So let's look at what we've done so far. A lot of work has been focused on mobility, reducing congestion, with traffic control strategies, and there's been a lot of talk about automated vehicles to solve this kind of problem. Same thing for safety. There's been a lot of work on safety. In fact, at the Automated Vehicle Symposium that I attended back in July, many workshops, actually there were more workshops on safety, especially from the manufacturers, than the mobility aspect. And guess how many were actually about emissions or energy consumption.
None.
Just one. I just attended one, that was the only one. But we really have to focus on this now with increasing demand from the population increase and more human activities. We really got to move people and goods more efficiently and really reduce or mitigate the impact that we have on the environment. As you can see recently, you hear news about hurricane. These are going to get stronger and more severe. Especially that could be a concern for the state of Florida and other coastal states. And this is why I'm going to break it down and talk about some of the details of greenhouse gas emissions for transportation. So transportation is actually a pretty large contributor. It's actually the largest contributor of greenhouse gas emissions associated with climate change. We're looking at almost 30%, 29%, more so than electrical power generation, industrial activities, agriculture, and commercial and residential use. And to break this down even further, it's actually coming from highways for the most part. So if you look at light-duty vehicles, that accounts for 59% of the emissions. And that's coming from your passenger cars, your SUVs, your pickup trucks that people drive every day. Same thing, also in addition to that, we have 23% coming from medium-duty and heavy-duty trucks that are moving freight every day. So on our highways, our local streets, add them up, we're looking at a pretty large chunk of the emissions, 82% to be exact. While other modes of transportation like rail and aviation are not the biggest contributors. So the focus really should be on our everyday travel, both in terms of moving goods and people for the highways and local streets. And we have been doing that recently with vehicle fuel-saving technologies. Direct fuel injection, for example, auto start-stop, that shuts off the engine automatically and restarts again to minimize idling. And in the past 15 years, we have seen a lot of progress in the area of hybridization using smaller engines, electromotor, and combining with battery pack, regenerative braking, and the auto start-stop system. And now the hype is about electric vehicles. However, this is not progressing as fast as we thought it could have been. 2% market penetration is still pretty small after 15 years of pushing for this technology in the automotive world. But besides the automotive aspect and the research on powertrains, we could definitely do more when it comes to mitigating our environmental impact in transportation. If you have an efficient car but an inefficient traffic condition, that's not really going to help the situation as much. Think about the difference between this and that one. If you have an efficient car that's relatively efficient overall, you're still going to see a big difference. In free flow traffic, you're going to get much better fuel economy than in congested traffic. Even with hybrid vehicles, the difference may not be very large, but there's still that loss in terms of acceleration, unnecessary acceleration and deceleration. And this is why we want to focus, and this is why I'm going to be talking about my recent project on how we improve traffic, how we control traffic for mitigating the environmental impact. In addition to pushing for better vehicle technologies to save fuel and reduce environmental impact. And I'm going to introduce you to this case study on freeway ramp metering that I did very recently with the Department of Energy under the Smart Mobility Program. And this was a joint effort with UC Berkeley and PATH. So to give you a quick overview of why we need to have ramp metering, what's the point of ramp metering in the first place, let's go back to the basics of traffic flow and freeway bottlenecks. There's a phenomenon called capacity draw. So what happens is that as you see merging traffic from the freeway on-ramp, as they enter the freeway, they're gonna, if the flow is very high, if the demand is very high, the large influx of merging traffic will cause a lot of conflicts, and it'll force the right lane vehicles, the shoulder lane vehicles to slow down, and there's going to be denser traffic and accumulation building up on the shoulder lane. As a result of that, normally people would just want to shift to the other lanes towards the left to avoid this denser accumulation in order to travel faster. And as a result of the lane changes, the median lane or the lanes to the left are going to have to are going to see vehicles that are decelerating, and they have to accelerate back again. So this kind of disturbance creates an issue called capacity drop, and it's a reduction in the the maximum flow of a freeway bottleneck as a result of a large influx of merging traffic from the freeway outlet. And this has been very well documented in the past 2 decades or so. This is just to give you some key publications regarding the phenomenon that we're talking about here. And this is why you see at freeway merges, there's a bottleneck, and merging traffic are piled up right here by the main line. Well, there is a solution to that. People have proposed this, and there's been a lot of empirical study done on this. And it's something called ramp metering, which we restrict the flow of on-ramp traffic to a certain rate that's lower than what you would get if they are allowed to merge on to the freeway freely. And to do that, we can, if we do that, we can actually prevent a large influx of on-ramp traffic from merging in a short amount of time. That reduces the probability of forming the accumulation in the shoulder lane and mitigates the lane changes, and therefore reduces the disturbance, and then can mitigate capacity drop. That's been done empirically, that's been verified empirically back in 2005 to show that it's effective, and it's effective in terms of restoring the freeway capacity. And just to give you an idea here, what the mechanism of congestion reduction is. So if we look at a input-output diagram, a queuing diagram here, we have the virtual arrival, as well as the departure at this freeway bottleneck. And the area between the 2 curves, the red and green curves, represents the overall delay. If we mitigate capacity drop and improve the capacity of the freeway bottleneck, we can make this area smaller. So the area between the green and, the red and the blue curve is smaller than the area between the red and green curve. And that will also generate less stop and go waves as a result of these, having fewer of these lane changes and accumulations. The question we're trying to answer is that now we have the mobility benefit, we spend less time for additional delay. Does that translate also less stop and go waves? Does that translate to lower fuel consumption now that we have less idling, as well as fewer unnecessary decelerations and accelerations on the freeway? Well, there's been some effort, very minimal effort done in this area, namely a study from Minnesota DOT that looked at this using a very rough estimate. It just basically correlates CO2 outputs with the number of stops and the stop time. That was not representative of the real world conditions, and nobody has really looked at what the real impact of ramp metering is on freeway environment, the impact of ramp metering on environmental impacts and greenhouse gas emissions, as well as fuel consumption. To do that, well, the most precise way if we to handle this problem is to actually go out there, collect lots of data on individual vehicles using their vehicle onboard computers. We all have this OBD port or onboard diagnostics port that we can plug into to diagnose problems with our vehicles, and the more advanced versions will actually get you information from the onboard computer, like fuel rate and throttle input and all sorts of detailed data that the automotive engineers are interested. But that's not very feasible, right? You can't go out there and hack into every single vehicle on the road and collect data. That would be the most accurate way to do it, but not feasible and very expensive. So we want to rely on a realistic simulation to be able to study the impact of ramp metering and emissions and fuel consumption. First of all, we have to have a good driver behavior model to be able to simulate something like capacity drop, and also to simulate what's going to happen once we put ramp metering. Is that going to mitigate capacity drop? On top of that, we need an accurate fuel consumption and emissions model that really captures the effect of stop and go waves and acceleration and deceleration in congested traffic. And we have to calibrate them and validate them to be able to represent the real world conditions through simulation experiments. First of all, with the driver behavior model, we have actually developed, one of my colleagues at PATH, Dr. Hao Liu also, and I have developed this driver behavior model to simulate complex freeway corridor behavior. This overrides a lot of the commercial software packages, and this does a better job and actually is able to simulate capacity drop. And we also modeled complex lane changes in congested conditions. It's done using a Microsoft development kit, and you can run that alongside a simulation software named NameSoft. And we were able to incorporate mandatory lane changes that involves exiting and merging, as well as discretionary lane changes that involves passing to achieve a higher speed. And we also added another component called anticipatory lane changes, the active lane change to the left in order to avoid oncoming merging traffic. And that happens in the real world. We made this model as realistic as possible. It is a little bit more compositionally burdensome relative to the commercially developed software packages. This was calibrated at a very complex freeway corridor with multiple bottlenecks in the morning peak. This is a 13-mile-long corridor in Sacramento, California. It's State Route 99. It has multiple of these cloverleaf style weaving sections, as well as a major off-ramp that actually has 50% of traffic using 2 of the lanes to exit and off-ramp right here. In addition, we have typical merging sections where one of the on-ramp lanes actually merges onto the freeway mainline lanes. So this is a speed contour plot for the calibration study that we did. This is a comparison of the field data as well as the simulated data. We were able to capture the general congestion pattern in the speed contour plot, both in terms of the duration of congestion as well as the length of the queue. There are some discrepancies as a result of variations in driver behavior spatially. So some people behave a little differently from one location to the other. And we did not want to over-calibrate this model to specifically for this particular corridor. We want to generalize a model that can simulate complex traffic conditions like capacity drop. So that's the compromise. This is why you don't see exactly the speed contour plot that you see in the field when you simulate it. And this is a representative bottleneck, and we were able to replicate the flow versus density relationship at that particular location. And these are data from 2 different locations. Moving forward to emissions modeling, what's been happening recently in this field is that we have a lot of people using the MOVES model or the motor vehicle emission simulator that's being developed and advocated by the Environmental Protection Agency. It's very crude in the sense that it can't capture speed fluctuation very well. It's an approximation. What you have to do with this model is in every simulation time step, you want to find the resistance for that vehicle, whether that's aerodynamic drag, rolling resistance, or grade resistance. You approximate this for that particular vehicle based on the instantaneous speed. You find that range, and you find a bin that corresponds to the particular vehicle-specific power after calculating the resistance and also determining the range of speed. And you go to this table or graph to find what bin you belong to and what the corresponding fuel consumption rate is for that particular operating condition. The operating condition, it tries to cover a lot of different scenarios. That the vehicle could be, accelerating between this range of speed and they will still have the same fuel consumption. So it's not the best and most accurate way to model something like capacity drop and the speed fluctuation and stuff, flow waves at a particular fluid merge bottleneck. And this is why we adopted autonomy, which is a model developed by Argonne National Lab. So this requires an input of trajectory data from the simulation into their MATLAB software and MATLAB-based software. And their model was developed using dynamometer tests that simulates actual wind and air resistance and for a variety of different vehicles from the factory. And this represents a good fleet mix or a realistic fleet mix of vehicles. Every 5 years it's being updated. And it accounts for the fact that there's only a small market penetration of hybrid electric vehicles and the fact that there are more and more SUVs on the road these days. So this is as realistic as I can go. It actually simulates the way how the engine performs. With every gear shift and engine RPM, you're going to have a different fuel consumption rate, and no matter what speed you're in. So, and this is done through parallel computing. It's more computationally burdensome, obviously, than the MOOCs model, but by taking a sample of the trajectory data from the traffic simulation, we can actually use this model, even at this very precise scale, to run the simulation and the analysis in a relatively short amount of time. Now we've talked about the tools. We've talked about how these models are representative of the real world. Let's look at the simulation setup that we have here. In this case study, we looked at a simple freeway merge bottleneck with 4 lanes of 4 mainline lanes on the freeway. First of all, we simulated the main line to determine the capacity of the freeway without adding any on-ramp demand yet. We put as much demand upstream right here as possible until we observe a queue and we measure the maximum flow. We increase the demand progressively until the maximum flow does not increase anymore. So that is the capacity of the freeway segment. And then afterwards, we start to add on-ramp demand at 300 vehicle per hour increments. And to add that, you will see capacity drop in the next few slides or so. We do expect the simulation to be able to simulate capacity drop. In fact, it actually did. So in this simulation, for an hour simulation period, the maximum flow remains pretty high at 7,700 vehicles per hour. So that's slightly less than 2,000 vehicles per hour per lane in this segment. As you can see with the other colored curves, at 300 vehicles per hour at a relatively small on-ramp demand, the flow, the maximum flow stays roughly the same. The capacity does not decrease, but at higher on-ramp demands, up to 1,500 vehicles per hour, starting from 600 vehicles per hour, we start to see a diminished maximum bottleneck discharge flow. So capacity drop has been simulated here in this merged bottleneck in the microscopic simulation. And this equates to roughly about a 9% reduction in capacity at the freeway merged bottleneck we're looking at. Well, if we look at this right here, at a low on-ramp demand, as low as, let's say, 400, we actually don't observe capacity drop. And really starts to pick up later on at the higher on-ramp demand, up to, starting from 600 vehicles per hour. What if we restricted the flow of on-ramp to 400 vehicles per hour? And that's when that's the highest you can go before you get to capacity drop, right? Let's restrict that and meter that at meter the freeway on-ramp at that particular rate so that the merge bottleneck improves and restores this high capacity that we see right here. So this is a comparison between before and after metering. So this is before metering. This is with the 400 vehicle per hour metering rate for all of the high on-ramp demand scenarios that we simulated, 600 vehicles per hour, 900, 1,200, and 1,500. You can see the capacity restored back to roughly 7,700 vehicles per hour. And we were able to mitigate capacity drop in the simulation. So the simulation is valid, and we can simulate realistic traffic behavior at a freeway merge bottleneck. And this is just to show you that a comparison between no metering and with metering, obviously the delay decreased on average, the average speed improved, as well as the total travel time decreased. And the total travel distance improved because the capacity is higher. And let's just do a sanity check right here. I talked about how the shoulder lane accumulation, or the density, increases when there's capacity drop, right? With metering, we were able to mitigate the capacity drop, and the shoulder lane density, or the accumulation, it stays relatively low, lower than the case without metering. And the number of lane changes stays relatively lower in comparison with the case without metering. So that shows the simulation is actually doing its job, and it's actually simulating the mechanism of capacity drop. When you put red metering, the simulation is simulating the fact that red metering is effective at mitigating capacity drop. Well, we talked a lot about mobility and congestion. How does that, the bigger question is, what are the results like for emissions? Well, it's what we expected. As we increase the on-ramp demand, higher and higher, there's more and more fuel being consumed on a per vehicle and per distance basis. We're looking at 57% increase in emissions. When it comes to adding high on-ramp demand, so at 1,200 vehicles per hour, we're looking at 57% increase in fuel consumption on a per vehicle and per distance basis, compared with the case without any on-ramp demand. And with metering, you can see there's a 20% reduction of fuel consumption as a result of controlling the freeway on-ramp flow and mitigating this disturbance from capacity drop. And as I mentioned earlier, we restrict the flow of on-ramp demand, so that could definitely increase delay and could penalize the on-ramp and improve the overall system capacity. And that is kind of similar here with emissions or fuel consumption. The on-ramp actually had more fuel consumed on a per vehicle and per distance basis in the case with metering, and the main line actually, or the on-ramp actually did not consume as much more fuel without metering. So this is kind of analogous to the red metering case for when we look at the mobility impact and the congestion reduction impact of it. We penalize some people that are traveling on the on-ramp in order to improve the overall system capacity. And you can see this with the CO2 output as well. Again, carbon dioxide emissions is correlated with fuel consumption. So obviously the pattern of increase and decrease and reduction, that's basically similar to the one for fuel consumption. And just to verify things here in this table, you can see that with stop time, it's correlated with the fuel consumption. So stop time is actually higher on the main line when there's no metering, and stop time pretty much goes to zero. The vehicles on the main line don't even have to stop and idle. So the stop time is defined as when they make a complete stop and they idle. And the number of stops actually goes away as a result of metering, because the overall capacity improved, and it's basically all going to the main line. And as I said earlier, we penalized the on-ramp. So the on-ramp actually saw significant increase in the stop time because they're waiting and idling at the red meter. It's literally a traffic signal that lets one vehicle go at a time. And you can see the same here. Everybody has to stop at least once on the on-ramp. So this is the number of stops and stop time per vehicle. Similarly, we looked at other metrics of emissions and environmental impact. Carbon monoxide is one of the important ones. It follows the same pattern as well as nitrogen oxide. And this is more true for diesel emissions, diesel vehicles. This could have a lot of implications for places with a lot of heavy truck traffic. Same thing for, same pattern for the particulate matter, PM 2.5. And this is typically associated with what you see in a lot of developing countries when it comes to air quality issues. methane gas is also associated with greenhouse gas emission, and that also saw the same pattern. So these are all related to fuel consumption, and when we put rent metering out there and improve the capacity of a freeway bottleneck, the environmental impact is mitigated and reduced as a result. So currently, this is just a proof of concept that I've just started about 5 months ago with a graduate student. We were looking at more realistic case studies at longer and more complicated freeway corridors. There's more work and interesting topics to be explored in the area of integrated corridor management, integrating traffic signals with freeway rent metering, so freeway control and arterial signal control, as well as variable speed limit and speed harmonization. That could have an impact, maybe a small impact on capacity, but maybe it could have a large impact on the environmental aspect of transportation. Moving forward, as we start to see more research and work and ideas about improving mobility with connected and automated vehicles, especially one of my colleagues, this is also my area as well, talked about adaptive cruise control and cooperative adaptive cruise control back in the seminar that was here in July. With the higher capacity, we could also see a lot of growth in terms of improving the environmental impact or mitigating the environmental impact of transportation. And that could be happening at arterials as well as freeways. And with level 2 automation, if automated merging could be very efficient and could be very good at managing traffic and improving capacity, it could also bring about maybe a significant reduction in environmental impact, fuel consumption, greenhouse gas emissions in the transportation sector. And also to mention that with the freight transportation, the impact may be even larger now that with truck platooning, now they're falling closer to each other. The aerodynamic drag is a lot less, and the stop and go waves are a lot less frequent. Last but not least, vehicle to infrastructure communication could also play a key role in terms of mitigating emissions. It could also be actively reducing emissions as one of the objectives, in addition to minimizing delay. And with a more realistic model like autonomy, we can study this in simulation and come up with a better and more realistic conclusion about what they can actually do to the environmental impact in the transportation sector. Lastly, I want to thank the project sponsor, the U.S. Department of Energy, and this Smart Mobility Program, as well as California Path at UC Berkeley, and Dr. Xiaoyun Lu, the program leader, and the PhD student I'm currently co-advising at UC Berkeley for the work that's been done. This is a working paper currently under review by the Transportation Research Board, and we are planning on submitting this work to Transportation Research Part D. So I want to thank everyone for taking the time. I'd be happy to open up for any questions, and follow me. This is my email and my Twitter account for my research group. Question? Yeah.
What exactly is automated merging?
So automated merging tries to minimize the disturbance from a large inflow of on-ramp traffic trying to merge onto the freeway, try to maximize the capacity of a merge, try to basically do a lateral control for the vehicles as efficiently as possible. With humans, it may not be the most efficient. So what I'm saying is, if we can improve capacity of a freeway merge bottleneck by better merging mechanisms, that could also have implications on the environmental impact.
Thank you.
Yeah.
It's a very nice presentation. I like your presentation style. Hope our students can learn from that. And I think in your result of energy consumption, you used autonomy from Emmerich's group in Argonne National Lab, I think. So we may go to more of the detailed sort of like I don't know too much detail about that model, but maybe they need to look into the acceleration, deceleration, stops, number of stops, that kind of thing, right? Is that
Right, yes,
So sort of more of microscopic models.
right.
And in order to do that, you might need to get vehicle trajectories, and you can get that from simulation.
Right, exactly.
But how to validate that? Do you, there is, because the reason I ask this is that we're currently working for Federal Highway Administration on a project using video to extract like trajectory data as we have extracted some trajectory data for I-75 about 2 miles section, but it was from, the bottleneck was an off-ramp, it's not an on-ramp. But we can do similar studies to collect such
Yeah.
data to really, validate to this. And it's also of interest from that group, Argonne National Lab. I met their folks at DOE meeting this year, so it seems like lots of folks are pretty interested in trajectory-based elevation.
So that's a great question. There's already some calibration done by Argonne Lab as they go through this process, as they're going through the model building process. They take a variety of different vehicle types and brands of vehicle, different makes and models, to kind of get a representative fleet mix of vehicles in the market. It's not the most frequent update. I mean, every 5 years things change, right? Technologies change. But this is as high of a accuracy as we can achieve at the moment.
I'm not talking about validating of the
Right.
autonomy model, but validating of your simulation results, for example.
Validating simulation results.
And to the trajectory level, that may impact, even if
Right.
their model is like 100% correct,
Right.
but if our simulation generates some errors in the trajectory, overall trajectory
Right,
values,
yeah.
that
That
could
could
be
happen,
run estimation. So I think, I think that would be of more of my interest.
Right, and that would be very helpful if we can, just taking a small sample of it doesn't necessarily have to be, all the trajectories. That could really correct some of the errors in the energy consumption and emissions calculation. Because, these are dependent on how many times you stop and the deceleration and acceleration characteristics. Yeah, we have not done that. That's up for the future work. This is a new phase of the DOE Smart Mobility project that just got started. We're also starting to gather ideas. We're still accepting ideas for the next phase.
Yeah, so maybe you can talk about.
Yeah, we can talk more
that.
about
And,
this.
Using your vehicles, you can do some probe tests, but that are just a small penetration rate.
Right.
But using video, it's like you can get the complete trajectories. That's probably some, and the drones are relatively cheap these days.
Yeah.
Also helicopters are also available.
Right. And I just want to mention, the results you get from one place versus the other, this is calibrated according to the
Yeah.
California drivers. It could be different wherever you go, so it'd be interesting to see. Yeah.
Great presentation, and I echo Xiaoping's comments that you all could learn from the excellent presentation style. And 2 questions. One was about the number of stops on the ramp vehicles. You had 1 stop per vehicle for the entering vehicles. So I'm just wondering if there were some assumptions made that there was no stop and go on the ramp? Because if you're inching forward, usually there would be perhaps many stops for the entering vehicle under the metering conditions.
Yes, there's an assumption in the simulation output. So once the vehicle is stopped and it's just inching forward, that's, the speed differential is really small.
Yeah.
It's not counted as an additional stop.
Okay.
But the fact that it's stopped from, let's say, 25 miles per hour is a big deal for emissions versus
Yes.
when it's just inching forward from 5 to 0 and then 0 to 5 again.
I was just wondering, I assume you had done some sensitivity analyses behind the scenes, but that might be an interesting, since that probably does figure in significantly to the emissions impact. It'd be interesting to see kind of a
Right.
sensitivity analysis of that.
Yeah, exactly. So the trajectory data is not, completely perfect, and that's the next step. this project just got started, so the next step would be to look at this in a more precise manner and really account for these minor or these little details
Yeah.
in the way how car following works in the real world.
So the second question is maybe more philosophical and maybe just to, having seen many presentations that look at safety and look at mobility and then look at sustainability, emissions, fuel consumption, and so on. And almost all of them are like yours, where there's kind of one picture and then you have all the different constituents of the emissions basically following the same pattern. And I just wonder, it feels like for those of us in transportation, we kind of say, well, oh yeah, emissions, they're always correlated with speed. I'm just wondering, are we missing an opportunity to communicate better about the emissions impacts of transportation, because this is how it always goes, that we have this one graph that sort of, I don't know, looks the same for all the different constituents. Do you think we're missing an opportunity to communicate better about emissions in transportation?
I think there's definitely more room for a better discussion. I personally think that maybe another way to communicate this kind of information is to really go back to that queuing diagram and convey the message that, well, the cars are running longer with more delay and because they're on the road more, and that's going to be an issue for sustainability. Instead of just talking about speed and trying to convince a lot of the stakeholders that traveling slower in congested traffic is going to be, the speed itself is a factor for higher emissions and higher fuel consumption.
Yeah,
I think that queuing diagram, that higher times or the longer time spent is a better message to say out there.
I think it's also, at least to me, it's abstract, right? Because
Right.
if you think fuel savings, right, you can convert that to dollars. If you have time savings, you can relate, oh, I saved 5 minutes. But nobody can say, what is a ton of CO2? I mean, how do you can't grasp that, right? So in Australia, they have this thing where they equated a ton of CO2 to some number of balloons. Everybody has seen like a person carrying a bunch of balloons. So there was some, I don't know, they were trying to humanize like what is a ton of CO2? How many balloons is that? So I don't know. I often wonder how we can improve the way we relate or connect people to understanding of the impact of emissions.
Can I add on that? I think in terms of illustrating the impact or the kind of outcomes, how that affects the emission from greenhouse gas. I think from our previous research, we find that when the carbon dioxide reduced and others, but actually nitrogen oxide is possibly increased.
Yeah.
So you do some kind of opposite directions of the different constituents in the greenhouse gas emission. And another thing is about how to convert that emission to maybe economic impact. I think there's some study or some standards used to saying, okay, if we have 1 pound of carbon dioxide, now how much money we have to spend to eliminate that effect? And same thing for other parts of the greenhouse gas emission. So, I mean, if you look into that table, you possibly could convert that into the dollar amount. And then to add that into the fuel consumption, so everything actually could be monetized.
Right.
Yeah.
Yeah, and I just want to make one more note that, with the emissions analysis, this is, because this is just getting started, this is under the assumption that, we're dealing with conventional passenger cars, gasoline engines. The NOx emission could be very different for diesel engines,
Right.
places with a lot of heavy truck traffic. CO2 may be reduced, but not necessarily NOx emissions. That's just the characteristics of truck traffic. Anything else?
Any other questions? No?
So only the professors ask questions.
Yeah, that's why, one semester what I did was actually I encourage students to ask questions and I record who's asking questions. And then whoever asks the most questions actually get a reward at the end of the semester. I think we should do that too. We should do that.
Yeah, when I was at Portland State, each student had to ask a question to get credit for the seminar.
Exactly, especially for those who register for credits. Come on.
The model, does it take into account only newer vehicles, or does it take into account older vehicles, since there are older vehicles that have lower emission standards, and the growing cost of cars, the disadvantage for a lot of people that can't necessarily afford the newest, most fuel efficient, so they just rely on an old Oldsmobile with the V8 catalytic converter hanging off, just spewing out. Does it take into account any of that for emissions and acceleration and that?
Yeah, it does take into account of, that's actually a great question, by the way. That does take into account of, the fleet mix, both in terms of the vehicle type and the vehicle age. It's updated every 5 years. Obviously, we're not going to get to the precise number of how many, what's that, like 0.2% of that old clunker is going to do, right? But, the fact that the average age of a vehicle on the road today is like 12 years old, so this is being accounted for. Surprisingly, fuel economy standards have, fuel economy has stagnated over the years, because people were buying bigger cars, and to compensate for the increase in fuel efficiency from technology, which is kind of unfortunate, but.
You notice an issue with people trying to merge? Like for me, different realm here. We have muscle cars and motorcycles, so when I have to pay a toll, I see how fast I can get to 60. Do you, for that, are there issues with people trying to merge? If there's, say, a slower car trying to catch up to speed, what's the that ramp? Do they typically have enough time to get up to speed for semi trucks? Rolling through 14 gears in their Allison transmission, or versus say someone in a Mustang or a McLaren.
These highway ramps are typically designed for these large design vehicles, but the issue, what I'm talking about right here is, what if we have a large number of them at the same, in a short amount of time, and that's when it creates a problem. You can never spend enough money on designing a highway for such large demand. If you do that, highways will be astronomically expensive. This is why we designed for the 85th percentile and the 90th percentile traffic demand, rather than that peak of the peak demand. Thank you everyone for the questions. Thank you for coming.
Thank you for
Thank
coming.
you.